Okay, so now we made it to the next section, which is encoding characters. Now you're starting to see a pattern now. You notice that I introduced some things to you early on because I was planting the seeds. So now we're about to add some more layers that help you really get the concepts. Now, if you're new to this content and you just arrived to the channel, the curriculum link is in the description. You can follow along if you would like. Also, too, if you haven't done so already, go ahead and subscribe and turn on your notification bell. Also, give a like and a comment. I'll look at the comments, and right now this is a new channel, so it's not a lot of comments yet. But as we grow, we'll start gaining in popularity eventually. So, but for right now, the focus is to help you to get to the next level. So we're going to be talking about encoding in this particular section of chapter 7. And again, you're seeing a pattern how early on I introduced some of these concepts to you, and we're going to keep adding new layers. So let's get into it. Now, encoding characters. If you have a microscope powerful enough to view the data stored on a computer hard drive or in its memory, you will see lots of zeros and ones. Each such 0 and 1 is known as a bit. A bit is a unit of measurement, like a meter or a pound. Collections of computer data are measured in bits. Every letter, image, and pixel you interact with on a computer is represented by a bits or by bits. We work with more complex data when our programs including numbers and strings. This section examines how such data is represented within a computer. Representing numbers. A byte, and we talked about this earlier, is a set of 8 bits, which is a collection. Bytes look like 00101101 or 1110011, and they represent a binary number or a base 2 number. So I introduced that to you earlier. A binary number is a number representation that uses only zeros and ones. The numbers that you are used to, which are built out of the integers of 0 through 9, are decimal numbers or base 10 numbers. Since each bit can have one of 2 values, each byte can have one of 8, equaling 256 different values. We're moving right along, aren't we? It may not be obvious, but every decimal integer can be represented as a binary number or a binary integer, and vice versa. There are 256 different values a byte can take. Which to represent a decimal integer from 0 to 255, because remember, 0 is an index, but yet it's an item to get your head around. So that's how we come up with 256. We will not go into binary decimal numbers conversion. If you're interested in learning more, there are many tutorials online that can show you the way. In this way, the bits in a computer can be viewed as integers. If you want to represent values greater than 255, just use more bits. Representing strings. Strings are collections of characters. So if we can represent each character as a number, then we'll have to go way, let me read that again. Then we'll have a way to go from a string to a collection of bits and back again. It gets kind of confusing saying bits and bytes sometimes. So bits. Character encoding. Unlike the natural translation between binary and decimal numbers, there is no natural translation between integers and characters. For example, you might create a pairing of 0 to A to 1 to B and so on. But What integer should be paired with a $sign or a tab? Since there is no natural way to translate between characters and integers, computer scientists have had to make such translations up. Such translations are called character encodings. Remember that word. There are many different encodings, some of which continue to evolve as our use of the data evolves. For instance, the most recent version of the Unicode character encoding includes emoji characters such as a taco. That looks like a taco. The ASCII encoding. Most of the characters that are using including letters, numbers, white space, punctuation, and symbols are part of the ASCII, pronounced ASCII, character encoding. This standard has changed very little since 1960, and it is the foundation of all the commonly used encodings. ASCII stands for American Standard Code for Information Interchange. But most programmers never remember that, so you shouldn't try to either. ASCII provides a standard translation of the most commonly used characters to one of the integers 0 to 127, which that's 128. Which means each character can be stored in a computer using a single byte. ASCII maps A, the letter A or lowercase a, to 97, lowercase b to 98, and so on for lowercase letters, with Z mapping to 122. Uppercase letters map to the values number 65 through 90. So capital A is 65, capital Z is 90. The other integers between 0 and 127 represent symbols, punctuation, and other associated odd characters. This scheme is called the ASCII table, and rather than replicate it here, we refer to you to a excellent online. So let's go there. And I want you to see that. Make sure you bookmark this because you're going to need it later on. So go ahead and make sure, if you haven't already bookmarked it, bookmark it. So now, in summary, strings are stored in a computer using the following process. 1. Break a string into its individual characters. Use the character encoding such as ASCII to convert each of the characters to an integer. Convert each integer to a series of bits using decimal to binary integer conversion. Here's a fun fact. JavaScript uses the UTF-16 encoding. It's good to know that, which includes ASCII as a subset. We will rarely need anything outside of its ASCII subset, so we will usually talk about ASCII code in JavaScript. Here's the character encoding script. JavaScript provides methods to convert a character into an ASCII code and back. The string method char code at takes an index and returns the ASCII code of the character that index. So here we go. We have LaunchCode string inside the nonprofit. If I go nonprofit.character code or char code at 0, it gives you the code. Here's the code right here. And so how does that work on our keyboard? When I press the keyboard, if I press it as a lowercase a, it sends out that code. So the lowercase a is at 1, it's 97. So it converts it to that value, and that value now converts it to whatever the binary code for that number is. And that's what the computer C. That's that low-level computer language that I've been talking about, that I planted the seed in your mind a couple of chapters ago. So now, to convert ASCII code to an actual character, use the string from char code. Here's another method that you can use. And then you start learning and understanding how to convert. I can convert all of these numbers. These are the ASCII encoding numbers right here, the values. And then when I use this from char code, and then I use, this is the syntax, paths and code, because here's the codes right here, here's the variable, here's the array, because this is an array. And I'll show you later on how to, when we get into the array section, how to identify arrays, and then pass it through, and then it gives you a word launch code. So you're going to have to play around with this code, of course, to understand it, but we made it to the end of this particular section. So remember, the more you do, the more you improve. See you in the next section.